Welcome to MEP 101. This is Module 4, Heating Systems and Equipment. Hopefully, if I don't get hit by a bus, I'll have Module 5 done for next week, and we'll do this again, just in time to go back to work. So today we're going to talk about heating systems and equipment. Some of the things we're going to talk about. A little refresher on heat transfer. We'll talk a little about sources of heat energy. Talk about burner-driven systems and how they're different from boiler-driven systems. We have an iPad waiting to get in. Hold on a second. Welcome, iPad. We will also talk about steam heating, hot water heating. We'll get into a little bit on heat pumps, and we'll finish up with a quick discussion on VRF systems. So, diving right in. Heat transfer. Remember, there are three. Well, we talked a little bit about in fundamentals about heat transfer from the human body, and there's evaporation was included in that. But the three main methods of heat transfer that happen in HVAC systems are convection, conduction, and radiation. Convection, as you might recall, is the transfer of heat through a liquid or gas. So as you heat that gas, it expands, gets buoyant, rises, and the movement of that fluid or gas actually spreads its heat to the surroundings or to anything that it comes in contact with. Conduction. Conduction is the transfer of heat through a solid material, i.e. the hot poker in the fire. Radiative heat transfer is the transfer of heat by electromagnetic waves from one surface to another, one hot surface to a cooler surface. Okay, just a brief refresher on that. Sources of heat energy. Where do we get our energy from? Well, primarily these days it's fossil fuels, although there's more and more renewable choices coming online. We typically will burn these fossil fuels in boilers or furnaces. Difference between a boiler and a furnace heats air and a boiler heats water. So you hear somebody say, my furnace doesn't work, and you go downstairs and there's a whole bunch of pipes connected to it. You know they don't know the difference. Another potential source of heat energy can be found in biomass, which is wood byproducts, even agricultural byproducts. People actually burn corn pellets or corn kernels rather in pellet stoves. So lots of different ways you can get heat out of biomass. The sun's another way you can get another place we can get heat from. Passive solar houses don't work particularly well in this part of the country, but there are places where you can completely passively heat your house with the sun by orienting it in a certain way and having certain materials and angles of incidence and things like that. Active solar, basically that's where you put some pipes up on the roof and let them heat up in the sun and use that hot water to heat. Also there's obviously photovoltaic. We don't do too much heating with that, but you can, in theory, take that electricity and say run a compressor for a heat pump. We can also get heat from the ambient environment. Outdoor can always be a heat source, even if it's colder than the inside. Again, using that refrigeration cycle we talked about. We can also pull heat out of the earth in terms of geothermal energy. And last but not least, there's always waste heat. Basically, rather than throwing heat out in the environment, if we can recapture it and reuse it somehow, we'll do that. Cogeneration refers to when you're generating energy, there's typically a lot of waste heat involved with that. You take that waste heat and use that as well. So two different types of systems use fossil fuels. The first we're going to talk about is burner-driven systems, and I call them burner-driven systems because the burner basically heats the end fluid, if you will. We release energy in combustion, and we transfer that directly to the space that we want to heat or to the airstream that's serving that space. So as a As a proud Italian, I can tell you the Romans invented the first radiant floor heating system. They also used it to heat up their public baths. Early burner-driven system. You can still go to Italy these days and see the remnants of those systems. They were called hypocausts. But in more modern times, some more modern examples would be your standard residential furnace. I guess that's not your standard residential furnace, is it? No, there we go. Couple different flavors of residential furnace. You can find a high efficiency furnace or standard efficiency. Standard efficiency gets you about 80% efficiency on your gas usage, but by some simple modifications to the basic design, you can improve that to 90 and even 95% in some instances. How do they do that? Well, in a standard efficiency furnace, typically a single speed, a single burner section up at the top, single speed draft inducer to pull the combustion products out and send them to the flue. What we do then to improve that is we add a secondary heat exchanger, and I would have actually changed this color from put the yellow at the bottom and the red at the top, because this part down here, the secondary heat exchanger, is actually the cooler part of the gas flow. So what we do is run the coolest air coming back from the house through this part of the heat exchanger, and that's where the vapor that's present in your flue gases gets condensed. And we talked about how when you condense the gas to a liquid, you basically pull a lot of heat out of it. So, and then we add variable speed blowers and variable speed inducer fans, and we really you can really fine tune a system like this to match the load in your house. Another more modern example would be your standard light commercial rooftop unit. Basically, this is a big air conditioner. You got a cooling coil on the way in, you go through a blower, and then you go through a furnace section on the way out. So this is where we burn the fuel. You'll find a little spout here that lets the flue gases out. We also have fuel-fired unit heaters that we use. A couple different models here. These have the vertical burner sections in them, whereas if you're tight for space, you can go with a low boy unit. They tend to be a little bit more expensive, burner technology. It's a horizontal drum and tube burner inside, but they're both driven by propeller fans. This type of heater we're actually installing right now, or has been installed down at the DCR North Point project. It's called a radiant tube heater. Your burner is located on one end. You send the products of combustion down through typically a ceramic or glass-based tube that heats up to basically red hot, and those infrared rays get reflected back off the reflector on the top and heat the floor directly below the heater. Now that's radiant heating only. That's surface to surface, so it really doesn't will not heat the air on the way by, but it will heat the floor, and the floor can in turn heat the air. By what? Convection. Biomass. Here's a pellet stove, right? Got one of these at my place. A little noisy, but they do the trick. And here's your original burner-driven system. Good old campfire. Fortunately, with this system, most of the convective heat gets wasted, goes right up into the atmosphere, but you get the radiant heat off the coals, which is why we like to sit around them on chilly nights. So we have two types of burners driven systems, two methods of firing, one called indirect fired. This is the most common type of burner driven system. It uses a heat exchanger to transfer heat to the airstream. This particular type is called that drum and tube I was describing. The burner would be mounted on this plate and basically force the flame into the drum. It hits the far end, turns around, and comes back through these tubes and then out to the flue. The other typical type of burner is called an in-shot burner. This is more like your gas grill type burner, arranged vertically, and it shoots flame into these individual tubes. And then there's an inducer fan on the other end that pulls the products of combustion through the tubes and sends it to the flue. This gives you an idea what it might look like in a rooftop unit. Going through an indirect heater on the top. How do I know it's an indirect heater? It's got a vent on it. Okay. So if you're up on a roof and you're looking at something, if it has a chimney coming off the top, it's definitely an indirect heater. If you don't see a chimney off the top, you still have to look for some places where gases could be venting. So on different units, they look different, but they could be very unobtrusive. This is the vent on this particular unit here. There's also, this is the little vent discharge on this rooftop unit. Let's talk a little bit about draft. What that really refers to is how does that combustion air make its way through the heater? So we have 4 different options. Natural draft is just like your fireplace at home. It uses the lighter gas, the heated up gases rise up through the stack, creates a vacuum, and that draws air into the fireplace or the furnace. Induced draft, basically this would be if you had a fan on top of your chimney blowing out, right, sucking everything through the system. Balanced draft uses a blower on the outlet as well as on the inlet to kind of balance the flow through. And then forced draft is only pushed from the inlet end. Okay. So there's a little graphic on how that works. Very descriptive, right? Get your chimney going there, fireplace, then you put a fan on the top for an inducer. 2 fans is balanced. Fan on the inlet is forced draft. The other type of burner that you're going to come across is a direct fire burner. In a direct fired burner, the products of combustion are actually mixed with the airstream. This particular model actually has bypass dampers on the top and bottom to modulate the temperature downstream of the burner. So this would be a fixed flow burner, 1 speed, and then you modulate the dampers to bring in more or less cold air. This particular one is a modulating flow burner, so it's got modulating gas valves on it, and that's how the output is controlled on that particular burner. Now you may be saying, you know, is this kosher? You know, we're putting products of combustion right into the air that people are breathing, and you know, one thing to think about is we do it all the time, right? Anybody who's got a gas stove at home is doing the exact same thing. The thing to remember is natural gas is mostly methane. It has small amounts of some of the other anes in it, about 90% methane, 10% other stuff. But all of those chemical or fuels, rather, if you burn them completely, you get CO2 and water. Neither of those obviously are toxic. I mean, the planet wouldn't exist without CO2 or water. That said, we have to be careful is with incomplete combustion. So when a flame does not get enough air, enough oxygen, instead of becoming CO2, it can only pick up, the carbon molecule can only pick up a single oxygen, becomes CO, which was, as we all know, is extremely toxic. So, I mean, I think for that reason, we typically don't see these systems, these types of burners used except in 100% outdoor systems. So we're pulling all fresh air across that burner, mixing all fresh air, not recirculating any of these gases typically. Most common place you're going to see that is on kitchen ventilation. So graphically, what that would look like, you have your fresh air coming in these diffusers right in front of the hood, and it gets just sucked right back out to the exterior. So short circuits, does not really get a chance to build up any kind of potential contaminants. Any questions on burner-driven systems? Ted, you look just totally engrossed. All right, moving on. Let's talk about boiler-driven systems. Boiler-driven or hydronic systems. But a lot of times we talk to engineers and they talk about hydronic systems, they're really talking about hot water or chilled water systems. But strictly speaking, hydronic does include steam as well. It's any system that's water-based, and steam systems obviously are water-based. So in a boiler system, the energy released from the fuel is actually transferred to a fluid medium for transport. Okay. Why would we use a boiler-driven system? Isn't it, why wouldn't we just want to transmit the heat directly to the space that we're trying to heat, or directly to the airstream that serves that space? Well, the answer is simple. Water and steam are very efficient means of transporting heat energy compared to air. So I can move the same amount of heat energy in a 2-inch pipe that would take me a 50-inch duct to do. So, when you talk about when space is at a premium, it becomes pretty obvious why we use water and steam to move energy around. A couple different types of boilers. We'll talk about steam boilers first. Steam boilers are classified as low pressure or high pressure. Low pressure being anything up to 15 pounds gauge pressure. Hot water boilers are classified as low or high temperature. So if you're up to 250 degrees or 160 pounds of pressure, that's a low temperature boiler. Anything above 250 or 160 is high temperature. We don't see too much of that in our business. You'll see that more in the industry rather. Boilers are also classified by the method that they're manufactured. They can either be cast or fabricated. Cast iron boilers or steel boilers. Steel boilers come in 2 basic types: water tube and fire tube. One thing about nomenclature in HVAC, they're pretty descriptive. So water tube boiler is just what it says. I have water in tubes, and I'm passing hot gases over the tubes. Fire tube boiler is the exact opposite. I have a big tank, and I'm sending the flame down through a series of tubes inside the tank. A couple of shots of water. This is the interior of a water tube boiler. So basically all they do is build a firebox around it, stick a burner on the end, and away we go, right? Burner would sit right at this end and blow its products of combustion down, back, and across all these tubes and go out the flue. I'm going to use a pointer, I think. That's a little fancier. Yeah, look at that. So fire tube boiler, like I said, is the opposite. We have a big old tank. We're sending flame down into a combustion chamber. It gets sent into a series of tubes, back and forth, several passes typically, and then out the flue connection at the end. So if you ever see a big tank like this, you can point at that and say, hey, that's a fire tube boiler in it. People think you're really, really smart. So cast iron boilers, on the other hand, are by definition water tube. Each of these cast iron sections is hollow, and water flows up inside them, and then the products of combustion are sent across the plates to heat the fluid inside the sections. So you can kind of see the blue is the cold water coming in, flowing up through each section, and then coming out the top is hot water. And then the combustion, you'd have a burner sitting here, blowing flames into the combustion chamber, and then the flue gases make their way out the back. This is what one would look like in real life with the cover taken off. And this is also just a point of discussion. It's also how they make steam, cast iron steam radiators, individual sections that are basically pulled together under tension, with gaskets in between. And anyway, there you go. Any questions on these different types of boilers? Okay, now we've gotten, boilers have gotten much more sophisticated over the years. We have condensing boilers, just like condensing furnaces. They work on the same principle. They'll use a secondary heat exchanger to reduce the flue gas temperature even further and suck more heat out of that flue gas. But they still operate on the same principles and are built essentially the same way as these boilers we just discussed. So, okay, Let's talk a little about what do we do with these boilers? We can make hot water or steam, right? So let's talk first about steam. Steam systems use the vapor phase of water to supply heat and kinetic energy through the piping system. What do I mean by kinetic energy? How does it do that? Well, steam water, when you boil it, expands 1,700 times its volume. So that alone, that expansion is the motive force to drive the steam through the system. It needs a place to go, so it finds its way out. We can use steam to heat conditioned spaces with the correct terminal heat transfer equipment, like a fan coil, for example, or an air handler, or we could also use it to heat water in the heat exchanger, which is then sent to radiators and whatnot. We also use heat exchangers, steam heat exchangers, to heat domestic hot water, and we use them quite a bit for industrial and commercial applications like laundries and kitchens. There's like a steam table. There you go. We use steam. We could also use steam as an energy source for certain types of cooling processes. We talked last week about the refrigeration process and how we use electricity to drive a compressor to take a cool refrigerant gas and pump it up to a higher temperature and pressure. So an absorption chiller just gets rid of the compressor and uses heat energy to increase the temperature and pressure of that gas. So you'll see absorption chillers on big campus type applications, hospitals, college campuses. You may find absorption chillers these days. Steam is ideal for district heating and campus distribution because basically it's the best way to send heat over a long distance. And steam systems come in two basic flavors: low pressure, which is under 15 pounds, or up to 15 pounds, I should say. That should be less than or equal to. And high pressure is anything over 15 pounds. Now, if you worked on college campuses or hospital campuses, places like that, you'll some of you are probably saying, well, hey, what about medium pressure steam? You know, steam systems are classified as low pressure or high pressure, but the way people use them, they have different descriptions. So, for example, at Harvard, they'll run their low pressure systems at about 10 pounds. Then they'll have medium pressure at about 45 to 50 pounds. And their high pressure system runs around 120. So for them, it's low, medium, and high, but they basically have two different classes or different settings of high pressure, which would be the medium and the high that they call it. Just a little bit of semantics. What are some of the advantages of steam systems? Well, like we said, steam doesn't need any pumps to move it through the system. That's the steam, not the condensate. I'll get there. I see it, Ted. You're waiting. You just happen to be the picture right under mine, so that's why you're getting all the shit. Steam systems do use relatively low volumes of water, and the steam that hits the first radiator is typically the same temperature as the steam that hits the last radiator. Can't necessarily say that about a water system. With a steam system, you can add or remove terminal units without making any basic changes to the design of the system. And you can actually, shut down a portion of the system and leave the remainder of it open much easier than you can with water systems, where you typically have to, shut down and drain the system to add something to it or take it apart. Steam systems do come with a downside. They generally aren't as well understood by end users or engineers, for that matter, as hydronic systems are. They do require more maintenance than hot water systems, especially the steam traps, which we'll talk about a little bit later. They definitely require more careful monitoring. Make sure that we're sending steam down the line at the optimum dryness, which is related to the pressure that you're sending down the line in. If it's too wet, which is basically saturated steam just above the boiling point, you can get a lot of corrosion and scaling. Little water droplets will carry chemicals and inhibitors with them, and they then get deposited in the pipes. Whereas dry steam, there are no water droplets. It's completely the steam is completely evaporated. Wet steam also increases the chance of water hammer, and it reduces the efficiency of your system. So, any questions so far? Okie dokie, we'll keep going. Let's talk about how we pipe a steam system. Typically, the material you're going to use for steam system is Schedule 40 black steel or carbon steel. For high pressure steam and for condensate lines, we'll use Schedule 80, which is a thicker wall. Condensate does tend to have some acidity to it, excuse me, and will basically corrode a pipe quicker than the steam side will, so they'll use the heavier wall on the condensate side to increase the length of the lifetime of the system. But more often than not, we're going to see welded fittings, although screwed fittings are used on some smaller piping. And it's very important to make sure that when you change size, we use eccentric fittings, because we need a flat bottom on a steam pipe at all times so that condensate can drain through it. In a two-pipe steam system, you want to make sure that the pipe is pitched downward in the direction of steam flow. There's the exception to that is the one pipe, which I'll show you. And we definitely have to make sure that our steam systems are well insulated, because the last thing you want to do is have condensate forming in your piping. You want condensate to form in the coils.
I got pulled into something, so I got to jump on work for a couple minutes.
Go for it. Okay. Where was I?
Sorry about that.
No problem, Will. And basically, the other thing you have to think about is condensate management. You have to have drip legs installed at all the low points and on your long horizontal runs, because condensate will form in the piping. It's unavoidable. We want to minimize it, but when it does happen, we have to take care of it and remove it from the system and get it back to the boiler. So, typical one pipe system. This is something you might have found in an old house, right? Cast iron radiators, boiler in the basement, single pipe going up and feeding all your radiators, and there's only one connection to the radiator, right? So steam goes in, condenses, condensate comes back out, same pipe. Steam's flowing this way, condensate's flowing this way. So, like I said, they use the same pipes. We have counterflow on the condensate. That can potentially cause problems if you have a lot of condensate, especially when systems are really starting up and condensate is forming like nobody's business because the radiators haven't heated up yet. You can actually overwhelm the pipe with condensate, and you get a slug of water. It gets pushed back against the end of the pipe. So if you're ever in an old building and you hear the pipes clanking, that's water hammer, okay? In small piping systems like this, water hammer's a nuisance. You know, it'll wake you up at night or whatever, just making noise. And it will, eventually cause some damage maybe to your air vents and things like that. But in large systems, water hammer can be deadly. I actually read an article in one of the engineering magazines several years ago about a guy who went down into a steam manhole to do some work, and this was a college campus, I believe, if I recall correctly, and somebody did not know he was in there and opened up a steam valve upstream and sent a huge slug of condensate right down into that manhole. And this moves at this, in fact, these things will move at the speed of sound. So imagine a 30-pound slug of water heading towards the end of a 6 or 8 inch pipe. It blew the elbow off the pipe inside the manhole that he was working on and basically cooked them. So it's something to be very concerned about, very careful with. The more common arrangement for steam systems that we're going to encounter is in our commercial world is a 2-pipe system. So simplified, it looks like this. in the commercial world, this probably wouldn't be a cast iron radiator. It'd be an air handling unit or a unit heater or something like that, or a whole series of heaters. But the point is here, I have the single supply pipe, I have a supply connection to the radiator, and I have a return connection from the radiator. The difference here is I have a thermostatic trap located at the outlet. Okay. What does that trap do? It basically holds the steam in the heating element. It doesn't allow it to pass down into the return piping. What does a steam trap do? It traps steam. You know, what does an air vent do? Vents air. What does a P trap do? That's another discussion. Okay. So where was I? So you can see basically down at the end of the run, I have an F&T trap, which is a specific type of trap which allows continuous condensate flow through it. We come back down here to the Hartford loop. That's just a little bend in the pipe which is designed to make sure that your boiler never loses its water. And that's it in a nutshell. Steam goes out, condensate comes back in a separate pipe. Okay. Nice thing about traps, they only allow the passage of liquid condensate, which basically allows us to modulate the flow to each individual radiator or heat exchanger or load. Disadvantage of a two-pipe system, more parts, higher cost, more maintenance, but they work a hell of a lot better. So there's your trade-off, right? So what makes a two-pipe system work is the steam traps. There's a lot of different flavors of those as well. A lot of, you know, the old timers had a lot of time to invent stuff, I guess. This is called these are thermostatic traps. So basically they use temperature to open and close. If I have condensate flowing through here, it's cool, so this stays open. If steam starts coming down, it heats up the fluid in this disc and pushes the ball shut so steam can't flow through. Similarly with the liquid expansion trap on the bottom, as condensate's flowing through, the liquid is cool, so the plunger is pulled back. When steam comes through, it heats up the liquid, pushes the plunger, and closes the valve. So those are operated thermostatically with heat, okay? We also have mechanical steam traps. One on the left is called a float trap. You can see why. Condensate comes in, the ball floats up, lifts itself off the little discharge opening, and allows condensate to flow through. On the right, we have an inverted bucket trap. Condensate can flow continuously through here. When steam starts to get into it, it lifts the bucket and closes the valve. It's that simple. When the steam stops flowing, eventually it makes its way throughout this little orifice. The bucket will fall again, and the condensate can flow by. Most common type of trap that we typically see is called a floating thermostatic trap. On the top, you have just a simple float trap. But this, you can see, it's actually got an arm. Unlike the other float trap we looked at, where the ball just kind of floats, this one's actually connected to an arm and a valve. This is very similar to your toilet ball, right? Up and down, open a valve. The difference between this one and the one on the bottom is it has this little thermostatic capsule on it, and that lets air out of the system. Remember, when a steam system is cold, when it's not on, right? There's no call for heat. The boiler's not running. It's empty, right? It's actually not empty. It's full of air. So I got my nice cold steam system. Somebody turns the thermostat up, and the boiler fires up, and I start making steam, and I start sending steam down that down the pipes. The air's got to go somewhere. This is one of the ways that it gets out. So it hits a floating thermostatic trap until it'll keep letting air pass out, and until it sees steam. And once that it says, okay, I'm at 212 degrees in here, I shut. Now nothing can get through except condensate, because the steam is trapped by the condensate at the bottom. Okay. Speaking of air, air vents are a very important part of steam systems. The steam systems breathe. So you got to make sure that you have an air vent. If you have one pipe radiators, that's why you have air vents on one pipe radiators, to let the air get out so the steam can get in. And then when the steam is gone, they let the air back in to replace it. So they kind of break the vacuum, as it were. So here's an example of a cast iron radiator with this one pipe radiator with a steam, an air vent on the opposite end from the inlet. So steam comes in, flows up, condenses, flows back out. As the steam's coming in, the air is going out. And then you also typically would have them on your mains down in the basement and various spots along the system. Quicker the air can get out, the quicker the steam can get in. So we mentioned a little bit about condensate. And I said we don't need pumps in a steam system, and Ted almost jumped out of his chair. So larger systems do require more sophisticated condensate management because you can't always drain by gravity. In fact, it's very rare that you can drain a large steam system completely by gravity. So for example, here, if I have a boiler system in the basement level, I got a bunch of equipment sitting on the basement level, and all the steam flows into my heater coils and comes out through my traps. And now I'm basically at the floor level. I can't pitch back to the boiler, so I have to go down into the sub basement where I get picked up by a condensate receiver and pumped back either to a feed water tank or directly to the boiler. Okay. Wrong one. And this is what a typical condensate receiver might look like. Big cast iron, blocky looking tank with some inlets on it. This would typically be vented to atmosphere. It has a pair of pumps for redundancy and an alternator on the top, which switches operation from one pump to the other to keep the pump life about equal. Pump usage stays, between the two stays the same. Okay. That's the basic components of a steam system. Any questions on that? Wow. I must say the superintendents are a much more vocal crew. All right, moving on. Let's talk about hot water systems. Hot water systems do use pumps to provide the kinetic energy and get the water to circulate through the system. We use hot water to heat spaces by means of terminal heat transfer equipment. That could be a radiator, fin tube type thing. It could be a fan coil unit, reheat coil. Usually very commonly used in air handling equipment. If you have a constant volume system, it could be your primary heat source. If you have a VAB system, typically that's going to have reheat involved, but you still have to preheat the air to a minimum of 55-degree discharge, so you'd have a preheat coil in your air handler. Hot water systems are definitely easier to design. Take it from somebody who used to design these things. If I had the choice, I'd rather design a hot water system. A lot easier, a lot less to think about. And they're easier to maintain as well. They are not, however, it's easy to retrofit. Like I said, if I need to cut into a hydronic system, unless we're really, really careful with where we place isolation valves and whatnot, I'm probably going to have to shut down and drain down my system. Isolation valves cost money. People don't always want to design them or pay for them. So, what kind of how do we make the hot water? I guess that's my question, right? You can use fuel-fired boilers. So you got your fire tube boiler on the left, cast iron boiler on the right. We can take steam and run it through a heat exchanger, or even high temperature hot water, run it through a heat exchanger and heat water that would be sent through the tubes inside the heat exchanger. Water comes in, goes through the tubes, comes back out, steam comes in the top, condenses, comes out the bottom as condensate. We can use geothermal heat pumps to make hot water. like I said, we can pull the energy out of the earth if we have to. Solar collectors is another method. This is an active solar system. All it is a bunch of black pipes on the roof. They get really hot. You can make hot enough water to heat your house, you know, make domestic water, all that stuff. These are a lot more popular in the southern part of the country than they are here, for obvious reasons. How do we get that water to move around the system? Typically, it's going to be an electrically driven centrifugal pump. In fact, almost exclusively, it's going to be an electrically driven centrifugal pump. These pumps come in all shapes and sizes. The good old standby is your base mounted end suction pump. Why do they call it end suction? I'll give you one guess. Okay. Somebody said, well, that takes too much room. I only have half that footprint. Okay, well, we'll weld an elbow on the inlet and give you a stand, and now it's a vertical end suction pump. Why they would do that rather than just install an inline pump, I really don't know. I'm guessing that the equivalent inline pump to that vertical end suction is probably about 2/3 the cost, but that's a guess. Inline pumps are everywhere. If you have a hot water heating system in your house, chances are you've got circulators like this little Taco job here. However, you know, you're doing some of the larger commercial jobs like we do, you're going to see arrangements like this. This looks to me like chilled water and condenser water. If I had to make a guess, it could be hot water and condenser water. Okay. Another type of a pump that is a close cousin of the end suction is the split case pump. What they do there is they have a double-sided impeller. So instead of coming in one end, you basically bring the water in on either side of the impeller, these chambers here and here, and it gets sucked in both sides of the impeller and then spun around and spit out the discharge, which are, what's the word I'm looking for? Concentric. So the inlet and the discharge are on the same line. The latest and greatest innovation in pump technology, manufacturers have started shipping pumps with VFDs built on, which does save quite a bit of hassle. A lot of saves some finger pointing in the field. I didn't get the VFD. I can't hang the VFD. The mechanical guy didn't give it to me. Well, there it is. It's sitting right on the pump, right? So wire the damn thing, will you? So, any questions on pumps? Okay, you guys are a very attentive audience. Tell Lauren you get a gold star. Let's talk about system piping. What do we use to pipe chilled hot water systems with, rather? Up to 2 inches, typically, we're going to use type L copper. The old way is soldered fittings. Nowadays, you're going to see a lot of ProPress. Okay. In fact, if you go work on some of the college campuses, they don't allow you to solder anymore unless you have to, unless there's a reason you can't use ProPress. Rich Waterman was quick to point out yesterday, so I told you those guys are more vocal, right? He spoke right up. What about brazing? I said, well, we don't do too much brazing unless we're talking about refrigeration systems or, you know, medical gas systems. But he did make a good point. Some, you know, really a good plumber or a good heating piping guy, he's got to run copper inside a wall. He'll take the extra time and effort to braze it because that's a joint that's never gonna go. Okay, you can lose a solder joint, you can lose a ProPress joint. It's rare, but it happens. Brazed joints, they'll be there long after we're gone, unless somebody tears the building down. If we get above 2 inches rather, so 2.5 inches and up, typically we're dealing with Schedule 40 black steel. In Boston, we do a lot of welded fittings. We have a very strong pipe fitters union. They like their welders, so they like to keep them busy. Okay. Sometimes the engineers will allow you to use Victaulic fittings, or which are grooved end fitting. Same type of fittings we use in, or very similar, I should say, to protection systems. Heat transfer elements. Okay, so we've piped the water out into the system. What are we piping it to? Could be to a coil in an air handling unit. Could be to radiators, convectors, right? This is panel radiator here, Runtal type radiator. That's how I met my wife. She was the sales rep. Little known secret. This is your standard slant. It's called a slant top enclosure. Very, very common in schools, places like that. This is known as a convector. It's basically one of these, except taller, and it creates a lot of air movement through it by its design, i.e. convection. And here you have a radiant ceiling panel. So this one will not give you any convective heat energy, but it will heat all the objects directly below it. Okay. We also use unit heaters and cabinet heaters. Right? Basically, we got a coil and a fan and a box. That's a unit heater. Cabinet heaters, we have a coil and a fan in a cabinet. We also use a lot of fan coil units in our business. What's the difference between a cabinet heater and a fan coil unit? Fan coil unit is designed to heat and cool. Typically, you'll have a hot water coil and a chilled water coil in there. In two pipe systems that use the same piping for heating and cooling, and just switch the water in it from chilled to hot. You might might end up with a single coil, but it would be a cooling coil that you run hot water through, basically. Up at UMass Lowell, we had a 2-pipe system and 4-pipe fan coils. Go figure. Also fairly common for us, especially our TI jobs, we got VAVs with reheat. So a reheat coil mounted in or right at the discharge of a VAV box. And you recall we talked in the air distribution class about induction units. That one was a cooling example, but you can also heat with these chilled beams, they call them, right? Put your primary air in, blow it out, and you induce cool room air across the heating coil. So far, so good? All right. So, put it all together is a very simple residential type hot water design. You have your heat source, your boiler, you have a pump to move the water around. You have heat transfer elements into radiators, a little fan coil unit, some panel radiators. You have a supply main around the outside here, and the return main comes around the inside, back to the boiler. That's a fairly simple system, but we also get involved with some fairly complicated systems. This one here is a diagram. It's a P&ID for a hot water system. This system happens to be heated with a steam heat exchanger. And here's my steam coming in, my condensate coming out, a 1/3, 2/3 valves arrangement. Anybody know why we use 1/3, 2/3 valves on a steam heat exchanger? No? I don't hear any volunteers, so I'm going to tell you. So steam, being that it's a gas, if you run it through a valve that's just designed to handle full load, as soon as you crack it off that seat, you can get more flow than you need. It's very hard to control. So they use 1/3, 2/3 valves, meaning the smaller valve is sized for 1/3 of the load, the larger valve is sized for 2/3, so that you have a smaller valve controlling smaller amounts of flow. Makes sense, right? This system is like I said, a little more complicated. This one happens to have a glycol feeder on it, so we must be sending something to an outdoor unit, something that might be exposed to freezing. Water comes out of the heat exchanger through a pair of pumps. Why do we have 2 pumps? In case one breaks. Go out to the load. Could be fin tube radiators, could be air handling units, fan coils, whatever. We come back. On the way back to the heat exchanger, we're running through an air separator. Very important to get air out of hydronic systems. Air causes corrosion and noise. We also have an expansion tank because unlike a steam system, hot water systems don't breathe. They can't breathe. They're closed systems. But when you heat water, we all know water expands when it gets heated. That expansion needs someplace to go. So that's why we have expansion tanks. Any questions on that? One quick point on very basic design concept for hydronic systems, hot water systems is direct versus reverse return. A direct return system is piped so that the first load, the first radiator, I was going to call these radiators for the sake of argument, the first radiator that gets hit is also the closest one back to the boiler. Okay. Whereas with a reverse return, a water molecule has to basically travel the same distance no matter which radiator it goes through. All right, so if I'm a water molecule here, I get a shortcut, right? If I go through the first one, but in a reverse return, doesn't matter which load I go through, I still have to travel the same distance. Why do we do that? Why is that beneficial? Because it does cost more. There's more piping involved, so it's higher cost. But it also, what it does is it creates an equal balance across each one of the loads. The differential pressure is the same here to here versus here to here, essentially. Okay, and that makes balancing a hell of a lot easier. Okay, so hot water versus steam. Why would we use hot water or steam versus the other, right? We know hot water is less complicated to install, more flexible. Okay, steam requires more space. Because you have to pitch your steam pipes, you have to have room for traps and things. You need more vertical space in your ceilings to accommodate that. Yeah, and they're just easier. Hot water is a lot easier to install. Your pipes can move up and down. You don't have to worry about pitch, any of that. It's also easier to control temperature with hot water systems. We don't typically require the same kind of rigorous chemical treatment in a hot water system as we do in a steam system. That's not to say that we don't treat hot water systems, but they just don't. You don't have to pay quite as much attention as you would with a steam system. Hot water systems definitely have fewer licensing requirements. If I'm running a steam boiler above 15 psi, I have to have somebody on staff, basically on site, while that boiler is running. Okay. However, if I'm moving steam across heat energy rather across a campus, I'm going to go with a steam system. Okay. Any questions on hydronics, hot water, steam? So far, so good. All right. How are we doing for time? Oh, all right. This was a little bit of a long one, guys. Hope I'll blow through heat pumps and VRF as quick as I can. So, heat pumps. We're not burning fuel with heat pumps, right? We're just using electricity. We use a refrigeration cycle just like we did for cooling. We use the refrigeration cycle to heat.
Andrei.
Oh, hello. So, your inside heated medium can be either water or air. Outside, it could be water, air, could be the ground, right? So remember from the, this might sort of familiar from the cooling discussion, but standard refrigeration cycle where the compressor sends hot gas to the condenser, which then sends that back to the evaporator and back to the compressor. So this is the standard cooling cycle: compressor, condenser, evaporator, and back. The only difference between that and the old basic refrigeration system we looked at is this thing right here called a reversing valve. What does that do? It reverses the flow of refrigerant and sends the hot gas to the inside where it can be used to heat, and then it sends that the cool energy. It basically cools off the outside. So think about it. In air conditioning, we're cooling we're cooling the inside and heating the warm outside. In a heat pump situation, when we're heating the inside and we're actually cooling the cool outside. So it could be 32 degrees out, and my unit outside is going to be trying to make that 32 degrees 30. Okay, I'm adding colder air to the outside. Pretty ingenious. I'm not sure why it took people so long to figure that out. So, what do the components look like? Well, your outdoor unit can look something like this. This might be, 12 or 18,000 BTU unit. This could be about maybe 60. If you're in a bigger system, you could have a whole bunch of, say, 120,000 BTU units or 10-ton units. It could also be water cooled rather than air cooled. In this instance, you see the refrigerant piping come in on the right side. It's transferring its energy to a pair of water pipes. Those water pipes could either go out to a well or to a ground source loop buried in the ground, or to a standard cooling tower. This is actually very similar to the system that is going in at Long Wharf. All of these outdoor or quasi-outdoor units would connect with refrigerant piping to indoor units. They can come all different shapes and sizes. You have cassette units that sit in the ceiling. You have ducted units of various types, console units, but they're not showing as the ones that sit way up on the wall. See those all the time. But they're basically just fan coils. It's a fan and a coil, maybe a filter, and all they serve to do is blow the air across the coil and get the either heating or cooling into the room. The latest innovation, I guess you would call it, in heat pump technology are called VRF systems. VRF stands for variable refrigerant flow. It was invented by a company called Daikin. Daikin actually calls theirs VRV for variable refrigerant volume. Say that 5 times fast. But they copyrighted VRV, so the rest of the industry uses VRF as a buzzword. What does that mean? Basically, you have a variable speed compressor, inverter driven, which means it also changes the electricity from AC to DC. Basically, the way that saves energy is by matching the amount of refrigerant flow to the amount of refrigerant needed to cool or heat the space. You have 2 basic types of VRF system. One is your standard heat pump mode. So it's basically a more efficient heat pump, but all it can do is either heat or cool at any given time. So you flip the switch on the thermostat from heat to cool, and that's what you get. The latest and greatest, and the one that engineers like to use, is the heat recovery mode. And what that does, allows simultaneous heating and cooling of different spaces. How does it do that? Basically, it basically transfers heat from spaces that need cooling to spaces that need heating, or vice versa. Bypasses the compressor. So if you're not running the compressor, or you're running it less, you're using less electricity. So think about it. If I'm in a unit, if I'm in a zone that needs heat, then the unit that serves my zone is going to be the condenser. So that's going to reject heat into my zone. Condensers reject heat. Then in another room that might need cooling, that unit's going to serve as the evaporator, which takes in heat or ejects cooling. Daikin's system uses 3 pipes from these little boxes, branch selector boxes, back to the outdoor unit. So you have a refrigerant pipe, a liquid pipe, I'm sorry, a gas pipe, liquid pipe, and a mixed flow pipe. Most of the other manufacturers, like Mitsubishi, for example, they use a 2-pipe system. But what happens is that it's almost de facto a 3-pipe because these boxes need drains, because you're actually doing the phase change between liquid and gas in these boxes as opposed to at the outdoor unit. So whenever you're basically condensing, you're going to end up with some kind of condensate on the exterior of a coil that needs to get drained. So, yeah, they're kind of quasi 3-pipe systems, I should say. But we see more and more of these. They're very popular, very energy efficient, and they're not going away anytime soon. So, and with that, I think that's my last slide, folks. So how we do? 105, not bad.